continue working on chapter 24, problem solving. And I will solve, I believe, 6 of these from different topics on chapter 24. The first one here, it is a 10 microfarad parallel plate capacitor with circular plates is connected to a 12 volts battery. What is the charge on each plate? How much charge would be on the plates if their separation were doubled while the capacitor remained connected to the battery? How much charge would be on the plates if the capacitor were connected to the 12 volt battery after the radius of each plate was doubled without changing their separation? Here I did like the solution in a very detailed way so that you will benefit from this. Even if this is a conceptual question on the exam, I want you to know how you can verify your answers using the relationships between the variables. The first one here, I am just having a schematic diagram. This is the capacitor 10 microfarads connected to the battery 12. Q is as easy as this, V times C, which is 12 volts times 10 to the negative 6 farads because it is microfarad. You have the option here not to change the unit, and directly you are going to calculate the charge in units of 120 microcoulombs. Now, of course, we know that C has to do with the area, and D, then I will say C1, it is epsilon 0 A divided by D1, because here in the second part, we're just going to modify D. Then for the second capacitor, we have increased the separation into 2D1, and therefore I can create a relationship between the two capacitances, C2 over C1, and from that I can get a relationship that is going to tell me that C2 should be 1/2 C1. Q1 equals V times C1 and Q2 equals VC2. Then the charge should be 1/2, like we can conclude here that it is going to be 1/2 of Q1, which is 60 microcoulomb. Now, the other when we are going, it's a circular, area, and therefore we know that area equals pi r squared. Then if you double, I will say A1 was pi r1 squared, and if you are going to double r, then this is going to be 2r1 squared, and this is going to be 4A1. Therefore, I wrote here that the area is going to be 4 times when you double the radius, because the radius appears in the area equation as r, as squared. Therefore, the area will be 4 times. Then C1 is epsilon 0 A1 over D. C2 is going to be epsilon 0 4A1 divided by D. We did not change D. And here I have just divided C2 by C1, okay, and many of these they're gonna cancel, and then I have that relationship between C2 and C1. Then I will say the capacitance will be 4 times, and therefore since Q equals V times C, therefore Q2 will be 4 times Q1, and that is going to be 120 microcoulomb times 4, which is 480 microcoulombs. The second one, it is about the second checkpoint here. It is about system of capacitors where we are going to calculate what is the equivalent and how much charge. And maybe like sometimes we have questions about charge, about voltage, and these, remember, when I was introducing the lecture, you need to know what is the, I will say, what is the constant value? Is the voltage is gonna stay constant, or the charge is gonna depending on which type of connection we are using. Here the figure shows a system of 4 capacitors where the potential difference across AB is 50 volts. Find the equivalent capacitance of this system between A and B. How much charge is stored in this combination of capacitors? How much charge is stored in each of the 10 microfarad and the 9 microfarad? Here, of course, like the picture is going to be something like this. The voltage is going to be connected here. Okay, and here I will say we can easily know that the 5 and the 8 are really connected in parallel. I want to make them one, and therefore I gave them numbers, like this is capacitor 1, this is 2, this is 3, this is 4. Therefore, C2 to 3, they are in parallel. Therefore, C equivalent is C2 plus C3. Then I added 5 plus 8 is gonna be 13. It's very helpful if you will be able to draw the network after calculating each equivalent, because so that you will not be lost. Now I have the 10 with the 13 with the 9. All of them are in series. Therefore, I can say 1 over C here is going to be 1 over, let me write C10 plus 1 over C13 plus 1 over C9. This is like more meaningful. Okay, and then for, here, therefore, I will say 1 over 10 microfarad plus 1 over 13 microfarad plus 1 over 9 microfarad. As I told you, I calculate always the, what is called the 1 over the value, the decimal. And then here I have 0.1 plus 0.077 plus 0.111 farad minus 1. And this is when you add all these decimals, is going to give you 0.288. And I will take 1 over this. Don't forget, this is one of the common mistakes, 3.47 microfarad. Now, in order to calculate the total charge, you are going to, I will say, this is C total. I will multiply C total by V, which is 3.47 microfarad times 50, which is 174 microcoulomb. I can leave here my capacitance in microfarads, so but my Q total is going to be in microcoulombs. Now, whenever I have capacitors that they are really in series, the calculated charge here, the total charge is going to be the same for all. The question is asking about the 10 and 9, and I will say a Q total is the same as for all series capacitors, and that is 174 microcoulombs, of course, but the voltage is different in series. Now, checkpoint 3. This one is really a long one because what I did, I added for you derivations to know how, from where I did have you use these, equations. A capacitor is formed from 2 concentric spherical shells separated by vacuum. The inner sphere has radius 12.5 centimeters, and the outer sphere has radius of 14.8 centimeters. A potential difference of 120 volts is applied to the capacitor. And then the question is, what is the energy density at R equal 12.6 centimeters just outside the inner sphere? What is the energy density at R here, sorry, R equal 14.7 centimeter just inside the outer sphere? For a parallel plate capacitor, the energy density is uniform in the region between the plates except near the edges of the plates. This is true for a spherical capacitor. All right, and now I will go over the solution, but just as I told you, I have added more than one derivation here because I want to show you from where I brought these equations, because they are not one of maybe the listed ones here, just showing you how that was done before. Okay, first I have a diagram here that is R1 and R2, and the spherical R1 is 12.5 and R2 is 14.8, and the voltage between the two plates is 120 volts. There is an example for 23.24.3 where we were able after that to calculate what is E, and going back also to other chapters. Here I have, this is the example here, 24.3, two concentric spherical conducting shells are separated by vacuum. The inner shell has a total charge plus Q, and the outer has the inner shell has a total charge plus Q and outer radius RA, and this outer shell has charge negative Q and inner radius RB. Find the capacitance of this spherical capacitor. Because of course, we are talking about inner and outer because it has a thickness. Then this is really here. This is the radius, the outer for the inner, and this is the radius, the inner for the outer shell. This one is positive, this one is negative. Now, the electric field and the electric potential between the shells are the same as those outside a charged conducting sphere with charge plus Q. I did solve this also in chapter, I believe, 22 or 23. Any point between the two spheres, we're going to find that the potential is going to be Q over 4 by epsilon 0 R. Then I will say the potential for the inner positive conductor at R equals RA with respect to that of the outer negative conductor at RB is VAB. We're going to subtract VA minus VB, and that is Q over 4 by epsilon 0 RA minus Q, which is the same charge, but negative, over 4 by epsilon 0 RB. I like sometimes to write 1 over 4 by epsilon 0 as K. And then here, this is algebra here. I added the fractions. And then I will say the capacitance is then Q over VAB, which is going to be this expression. I am looking now for U, which is the electric energy density in vacuum. E here, it is the magnitude of the electric field. And from what I did here, I did calculate what is VAB. And I know that from example 22.5, E, it is for this, for spherical distribution, it is 1 over 4 by epsilon 0 Q over R squared. This is electric field outside a charged conducting sphere. Then I write it in terms of the, the the sphere that I have, E is 1 over by epsilon 0 Q over R squared. And what I did here is I did use this expression here to find out what is Q. And then I have Q in this equation here. And therefore, I was able to calculate E, the electric field, as RA, RB divided by RB minus RA multiplied by VAB divided by R squared. Then here I found an expression for E for this, I will say arrangement. Now for R, which is 0.126 meters, I have plugged in R here, and then I found E as 6.08 10 to the 3 volts per meter, and then I calculated EU as 1/2 epsilon 0 E squared as 1.64 10 to the negative 4. And also I did use that for R equal 0.147. I converted into meters. Then I have calculated E and then U again. Now for part C, is talking about here that for parallel plate capacitor, the energy density is uniform in the region between the plate except near the edges of the plate. Is that also true for the spherical? And now the spherical, of course, is different, and I will say no. And I will say, from the results from B, you can see the results from A and B show that it is not the energy density, it's not the energy, it did not give us the same number. Energy density is uniform. The reason is E decreases or changes as R increases, and therefore U decreases as well because it depends on E squared. Okay, now the dielectric to be used this is checkpoint 4. The dielectric to be used in a parallel plate capacitor has a dielectric constant of 3.60 and dielectric strength, this is the maximum. Remember, electric field, 1.60 10 to the 7 volts per meter. The capacitor is to have a capacitance of 1.25 10 to the negative 9 and must be able to withstand maximum potential difference of 5500 volts. What is the minimum area of the plates of the capacitor may have? Now I wrote here the quantities. Electric constant 3.6, the electric strength, which is E maximum, is 1.6 10 to the 7 volts per meter. And then we know that V is going to be E times D, and therefore I can calculate D as V divided by E, and that is the distance that I'm looking for. The capacitance now, I have a dielectric, then it's going to be K epsilon 0 A over D, and therefore I will be able to calculate A as CD divided by K, or kappa, sometimes we call it epsilon 0. We call it kappa most of the time, this constant. And then I was able to calculate that area. which is the question is asking about the minimum area that we need to have here. All right, now another example here, and that is with dielectrics as well. We have parallel plate capacitor has placed with area 0.0225 square meters separated by 1 millimeter of Teflon. Calculate the charge on the plates when they are charged. Potential difference of 12 volts. Use Gauss's law to calculate the electric field inside the Teflon. Use Gauss's law to calculate the electric field if the voltage source is disconnected and the Teflon is removed. Of course, here I have recorded my quantities here, knowns, unknowns. My A, my D, my Teflon is K kappa for it 2.1, and the voltage is 12. I will be able to calculate Q as C times V, and C, it is this all together. Okay, and then I plugged my numbers, and then this is the capacitance. This is the charge Q, 5.0210 to the negative 9 coulombs. Now, when I apply Gauss's law with then the dielectric, remember we said we're gonna create Gauss's law where like half of it, this is the plate, and this is the dielectric. And we said K times E times A equals a Q free enclosed free divided by epsilon 0, and then my E is going to be the Q free divided by A kappa epsilon 0, and then I did plugged in my numbers, and then this is 1.2010 to the 4 in Newton per coulomb. Now, without the Teflon and the voltage source, the charge is unchanged. Remember, we said when we are going to introduce or bring in the dielectric, what's going to happen? The charge is going to stay the same, but the potential is going to decrease. Then when I remove the dielectric, the charge is going to be unchanged, but the potential is going to increase now. C equal epsilon 0 A over D, and using Gauss's law now without a dielectric, E times A equals Q over epsilon 0. Then I have calculated the new capacitance here, which is epsilon 0 A over D, and that is 1.9910 to negative 10 farads, and then V, it is Q over C, which is 25.2 volts, and I can calculate E to be Q over epsilon 0 A, and that is really the new electric field. Now, this one is extremely important also. The capacitors in the figure are initially uncharged and are connected as in the diagram with switch S open. The applied potential difference VAB equals plus 210 volts. What is the potential difference between C and D, like here, between this point and this point? What is the potential difference across each capacitor after switch S is closed? And how much charge flowed through the switch when it was closed? Now, simply here, I did they give us like very easy numbers. Now, when the switch is open, as if there is nothing in the middle here, then here I will say 3 and 6 are really in series. Then I can find their equivalent as 1 over 3 plus 1 over 6 equals 3 over 6. Then their equivalent is 2 microfarads. And the same for 3 and 4. The equivalent is going to be 2 over 2 microfarads. And then I will, like in between these two, I'm going to have this one, 2 microfarad, and another one, 2 microfarad, and these are in parallel, and therefore C total is going to be 4 microcoulombs, 4 microfarads. Then now Q total, it is 4 microfarads times 210 volts, which is the voltage. Then the total charge is 840 microcoulombs. In all these network, sometimes you need to work backwards. Then here I did go backwards from here to here. Okay, I know that I have the same voltage. Then here I have 210 volts, and here I have 210 volts. And then I will be able to calculate Q for the 2 microfarad on top, and the 2 micro, of course, is going to be the same. Then each is going to have 420 microcoulomb. Remember, you might have different capacitors, but in this problem here, it's easier because we have the same, okay? But each time if you have two different values, then you're going to calculate the Q here, you're going to calculate the Q here. Now each capacitor, and now again going back to the arrangement where we have this. Okay, each capacitor, the 3 and the 6, has, of course, has 420 microcoulomb, because they are in they are in series. Then I can calculate V1 or let me say V3 for the microfarad. Then its voltage is going to be 140, and I'm going to calculate V6 for the 6 microfarad. Either you can say the same equation, 420 divided by 6, or you can say it's the difference between 210 and 140, and that is going to be 70. Then in order to calculate VCD, I will say it is VAD minus VAC, and that is going to be 140 minus 70, and that is going to be 70 volts. Now, when the switch is closed, okay, we are going to have that wire here. Okay, therefore, now the arrangement is different. I will say these 3 and 6 are in parallel, and these are really also in parallel. Okay, then you're going to add, that is going to be 9, okay, volts. And that is going to be 9 volts. And then I will redraw this. Okay, then I'm going to have 9 and 9 connected in series. And then I can say here 1 over C equals 1 over 9 plus 1 over 9. Then C is going to be 4.5 microfarads. When they are in, I will say, series, and they are equal, you can divide the value of C by the number of them. Q total is going to be C total times V, which is 945 microcoulomb. Each of the 9 microfarad will get 945. Therefore, their voltage each is going to be 105. Then they're going to share it equally, 9 and 9. And now with the switch open, okay, now this is like I calculated part B. Now for the last part, we are talking about the charge that did flow through the switch. When the switch is open, all have the same charge. Therefore, the Q net is going to be 0. And therefore, because the positive and the negative, they're going to cancel. With the switch closed, a Q3 is going to be for the 3 microfarad. It is 315 microcoulomb. And for the C6 is going to be 630. And therefore, the net charge is going to be 630 minus 315. And therefore, the net is going to be 315 microcoulomb. coulombs. Thank you very much and have a great day. This concludes chapter 24.